All right. Hi, Multi. How are you? I have to say, I'm a little bit sad that I'm not with you today to kind of continue the mind blowing moment that we left class with. But let's just pick up where we left off. Where we left off was a little ahead of this, I realized, but I wanted to make sure we kind of just very thoroughly backtracked where we left off. The directional derivative of f at x naught y naught in the direction of vector u, where u is a unit vector, is this set of partials multiplied, right, using the chain rule. And then remember that x is x naught plus su1, y is y naught plus su2. We made the observation that dx, ds, and dy, ds are always u1 and u2 correspondingly, which is actually very nice. And we left with this, and I think the very last thing I did on class when I saw you last was I rewrote this expression as a dot product of two vectors. And I called one vector vector u, since that is right here the components of vector u. And then I called the other vector this vector. And I left with saying this is a vector whose components are partial derivatives. And this is a very unique thing, a vector whose components are partial derivatives. And I think I may have even left with telling you what that vector is. A vector whose components are partial derivatives is called a gradient vector. I may have given you the symbol because I have a vague recollection of having an argument about an upside down triangle versus a right side up triangle. A gradient vector. Okay, and a gradient vector is symbolically, I should write this, a gradient vector of f of x, y. Okay, we can call it the gradient vector of f of x, y, or we can call it a vector whose components are the partial derivatives of f of x, y, or we can symbolically refer to this as its with its proper nomenclature, which is this. Okay, and the way you say this is you call this del f of x, y. And whenever you say the words del f of x, y, that means the same thing as the gradient vector of f at x, y, which means the same thing as the vector whose components are the partial derivatives of f of x, y. So now I'm going to go and refine this statement one more final time and say that this is equal to the dot product of the vector del f and u. And let's not forget what this all meant, by the way. This all equaled the directional derivative of the function f at the point at x naught, y naught in the direction of vector u. And if I were to be a little bit more precise and careful with my notation, I would write the directional derivative of f at x naught, y naught in the direction of vector u is the gradient vector del f evaluated at x naught, comma, y naught, dotted with the vector u. And here you have your final, most succinct and most user-friendly version of the directional derivative. So what I'd like to now do is work through a couple of questions that use the del f version of the directional derivative, and we'll kind of do this in a layered way. We'll start with something fairly straightforward and we'll move onwards from there, okay? Okay, so here's a question that's a pretty introductory one now that we have this new definition. I just said let f of x, y be this surface here. A is evaluate del f at 1, comma 2, just means just evaluate the gradient vector at 1, comma 2. Find the directional derivative, okay, using our definition above in the direction of vector u here, definition of above being here. Another particle located at 3, 1, f of 3, comma 1 heads toward 1, 2 heads towards 1, 2, comma f of 1, 2. What is the initial rate of elevational change? Obviously, I put this in quotes because z isn't always corresponding to elevation or vertical movement, but here I'm just letting it refer to as such. Okay, just try this one. This is a fairly basic question. Just go ahead and work through it and then replay me for the answers. And here are the answers right here. Okay, fairly straightforward. Part A, I just found the general gradient vector, and then the gradient vector evaluated at 1, 2. Okay, notice something here I want to tell you. Del F means the same thing as del F at x, y. This is often dropped, right? Like in text and notationally, we often drop it just to write del F. You do have to make sure, though, that when you are inputting specific x and y values, that you then, in this part, this can be dropped, this cannot be, okay? You have to say del F evaluated 1, 2. But this shorthand here, everyone recognizes as just the general del F at some variable x, y. Okay, you'll notice I did unitize that vector already for you. Happy face. So then this is the directional derivative right here. Okay, obviously, and maybe this is not obvious, but in case you're, just to be clear, the gradient vector is not to be unitized, okay? All right, so the directional derivative is negative 10 over radical 2. So initially, at that point 1, 2, f of 1, 2, its z value will decrease by this amount for every 1 unit it traverses in the direction of vector u, which is very nice. Part B, notice what I did here. This is the vector that refers to the direction in which you are heading from that point 3, 1. Notice here you do have to unitize it. Here is del F evaluated at 3, 1. The directional derivative then in the direction of vector u here is going to be this dot product, and here it is, your initial rate of elevational change. Okay, all right, let's continue with our part 2. So here is a question I want to ask you, which is this. We now have this wonderful expression, right, which looks like this in its most short, succinct version. Okay, and I want you to just kind of take a moment and just like appreciate that the directional derivative, we were first evaluating this in the most arduous, kind of algorithmically and arithmetically painful way, very long-winded, right? And now we have this really nice, succinct, version of the directional derivative. And don't forget what the directional derivative represents. It represents the slope of the line tangent to your surface if you were to travel in the direction of vector u. Okay, so this entity right here, right? Don't forget, like this dot product here, really, it refers to kind of slope, but I want to put in air quotes here. It's like the slope, it's a slope of the line tangent to the surface if you were to travel in the direction of vector u. So talk to me, well, actually, no, you can't talk to me. Talk to each other for a second about the relationship between the angle between this vector and this vector, because these are two vectors after all. Talk to me about the relationship between the angle between these two vectors and the maximum and minimum value of the directional derivative. In other words, is there a relationship between the angle between these two vectors and the maximum value that the directional derivative could be? Before I have you just kind of cogitate on that in your little groups, I want to remind you of our old friend from back in the day. Cosine of theta equals v dot w over magnitude of v times the magnitude of w, okay? And maybe you'll look at that. So again, the question is there a relationship between the angle between these two vectors And let's just start with the maximum and the maximum possible value of this directional derivative. Go ahead and talk about it. I really do want you to talk about it. If I were with you right now, I would say, here's a moment to experience like that exquisite agony. And I think the exquisite agony of romance, right? I can't think of anything else. If you can think of anything else, please tell me. Okay. Please talk about it and then replay me for a full explanation. Oh, okay. Okay. So notice the following. So here is, you've all kind of talked and argued, I hoped, but notice the following. If theta equals 0, okay, and all I'm going to do here is if theta equals 0, v dot w equals this positive number, because this number has to be positive right here, this positive number times positive 1, because cos of 0 is equal to 1. If theta is 180 degrees, v dot w equals this negative number, again, because this is a positive number times negative 1. So in other words, if theta equals 0, cos theta is at its maximum value, right? Okay, so we're going to focus on this pink statement first. If theta equals 0, cos theta is at its maximum value of 1 times this positive number, that will give you, in other words, 1 times this positive number represents the greatest possible value that v dot w can attain. So what does that mean about the directional derivative? The greatest possible directional derivative occurs if u and del f are pointing in the same direction. If these two vectors are pointing in the same direction, that means that theta equals 0 degrees. Okay, so what I'm trying to get you to think about here is the following. Let's say we were back to this question above, which says, where am I? Here we go. Okay, f of xy equals 2x squared y minus xy cubed. And let's add on to this now. And let's say that you are at the point f of 1, 2. And my question now to you is, you are at the point, okay, so you are located at the point 1, 2, f of 1, 2. And now my question is this: in which direction? In which direction? So here I'm not giving you the vector. In which direction should you head in order for your elevational change to instantaneously increase by the maximum possible value? In which direction should you head to obtain the maximum initial elevational change? Okay, so this idea is going to take a few minutes at the very least to gel. What I'm asking you here is, what is the vector that represents the direction you should head in for your directional derivative to be at the maximum? What we just discovered down here is that this vector u excuse me, which is the direction that you head in, correct? If that vector u was in the direction of del f, the directional derivative here will be at its maximum. So what I'm going to do here is say, well, what was del f at 1, 2? Del f at 1, 2, and I did the work in part A, del f at 1, 2 was equal to 0, negative 10. So what this is saying is, so you should head, well, actually 0, negative 10 is just directly south, right? Directly southbound. You could write, in this case, I just said directly southbound because 0, negative 10 is just clearly this way, but you could also say, so you should head in the direction of vector 0, negative 10. that's the direction in which you should head. And if you head in that direction, what will your directional derivative be? Okay, so now that's my second question to you. Now you've answered the first question A of this investigation. If you head in this direction, you know your directional derivative will be maximum. Now my question that I want to ask you to think about is, and what will that max initial elevational change be? Okay, so now that you know, okay, let's pick it up over here. What I'm asking you is, now you know that above, I know I'm kind of going in various directions here, but I'm going to pull from the work we did above. Del F at 1, 2 is equal to 0, -10. So clearly you should head in this direction for max elevational change. My question now that I want you to think about is, what is that max elevational change going to be? Like, what is that actual value? Okay, folks, so what I did here, I worked it out, and then I leave you with what's this called when you end something and you want to keep something like on the edge of their seats? What is that called? Oh, I leave you with a cliffhanger, okay? It's not even a major cliffhanger, but here it is, okay? This is the answer. That would be the max elevational change. And I say, but is there something shorter? Hint, point, okay? All right, I put your homework on the teacher page, and there is a quiz on Monday that covers just 3 things. Partial derivative, the chain rule, directional derivatives, and there's a third thing, and it just escapes me. Oh, local linear approximation, okay? The gradient is not fair game for the quiz. However, the directional derivative is. So if you're wondering, can we use the gradient if I ask a directional derivative question? The answer is yes, because it's much shorter. But again, any question that I give on Monday for the quiz, it cannot require the gradient per se. All right, so you've got everything you need. Please say hello to Miss Green and say hello to, well, each of you in the class, and I'll see you Monday. Goodbye.